So yeah, thank you, Dr. McMahon, for the wonderful introduction. So as Dr. McMahon talked about briefly, our group is working on developing a hybrid quantum classical graph generative adversarial network for generating chemically stable molecules via Python molecular benchmarking processes. So I'm Adelina, and today I'm joined by Max, Linda, Haset, Aditya. Unfortunately, Dia couldn't make it, but Falak and Lena are also here. So with that, let's get started.
So typically, drug discovery is an extremely expensive and time-consuming process. As diseases become increasingly complex, the process becomes even more difficult. As a result, scientists have been using computational methods such as machine learning or chemical simulations to speed up the research process. One promising method is the Generative Adversarial Network, or GAN. A GAN is a machine learning algorithm consisting of two neural networks, the generator and the discriminator. The generator is responsible for creating realistic fake data, and the discriminator is responsible for distinguishing between real and fake data. These networks compete against each other to improve the generation of realistic data. As the generator improves the data generation, the discriminator also improves that detection. Over time, the generator will create fake data that's so realistic, the discriminator will not be able to tell the difference. The goal of our research is to leverage quantum principles to create a generative model that will create valid molecules for drug discovery much more efficiently than classical models.
So for some context, we're going to talk about the very first iteration of our model that we've done. So the very first iteration of our model was known as the Quantum Generative Adversarial Network, otherwise known as QGAN. This model processes high-dimensional data efficiently via quantum superposition and entanglement, which are two quantum properties that allow for storing exponentially more data, as well as performing parallel computation. Beyond that, we use the QM9 dataset, which contains 134,000 small organic molecules represented in terms of XYZ files. The term XYZ files simply means that the files contain both the list of atoms in a molecule as well as each atom's X, Y, and Z coordinates. Within the quantum generative adversarial network, there were two parts. The generator used parametrized quantum circuits to generate atoms and corresponding X, Y, Z coordinates, while our discriminator was a plain classical neural network which classifies molecules as real or fake. One quick note, the reason why we decided to keep our discriminator purely classical was because the task of binary classification is already highly optimized in classical computing, and unlike the generator, which requires a lot of heavy computational usage, we simply didn't see a need to utilize quantum computing for our discriminator. As for our results, we had 300 total generated molecules, 7 of which were chemically valid. Now, it's important to note this was valid in terms of the atoms, but not the coordinates, and this corresponded to about a 2.33% success rate. The reason for the success rate being so low is because we have to sacrifice accuracy for computational power, as there is not much public access to quantum computers yet. Nevertheless, it is a promising start. On the right, you'll see a QR code to our paper, as well as some of our sample molecules, which kind of look like scatter plots. And there, as you can see, are not really any bonds between any atoms yet.
Okay, so QNetGAN is our second model, and it is an upgraded version of QGAN, which incorporates elements of NetGAN, a classical GAN that uses long short-term memory cells to generate graph-based data via random walks. LSTMs process data recurrently and are well suited for learning sequential data, and this makes them really good for GANs. And hence, QNetGAN used the abilities of LSTMs to generate molecular graphs. And this also helped enforce atom connectivity, which was a problem we faced with the scattered atoms from before. And in QNetGAN, the classical discriminator still has the same task of binary classification, but it can also use the LSTMs to learn better from its mistakes. So as with QGAN, QNetGAN was trained on the graph version of the QM9 dataset, and this time generated molecules were verified using Lipinski's rule of 5, which is a set of criteria to determine if a molecule can be a suitable orally active drug. And so thanks to LSTMs, QNetGAN now has an accuracy percent of 47, a lot better than 2.3. However, if we do quick calculations, we see that 47 is less than 80. So our goal of at least 80% accuracy was not achieved, and more work had to be done. So on this slide, you can see some of the molecules that QNetGAN generated. And while they are connected, most atoms are not connected according to the rules of chemistry. For example, we have this hydrogen magically forming 4 bonds over here, and another oxygen that is bonded to 2 oxygens, 2 nitrogens, and a hydrogen. It's pretty illegal. These are just a few examples of the goofy molecules that QNetGAN has produced. Also, you'll notice that our molecules do not have any double or triple bonds. And while they form like square and like triangle cyclo shapes, these aren't like realistic. Work is currently in progress to renovate these molecules so that each atom satisfies the octet rule and so that they become 3-dimensional. But before we talk about some of these upgrades currently in progress, it's important to compare our models for a bigger picture.
As you can see in this slide, we have a chart where we benchmark our various models. The NetGAN is the classical model and has a computational efficiency of 45 to 60 minutes, meaning that the model trains and reaches convergence in this time. Additionally, it requires around 8 gigabytes of memory. Although the accuracy is high, the classical model uses a lot of resources. QGAN, however, has a lower accuracy and uses more memory, but takes 30 minutes and has 120 quantum gates. 120 is a very high number of gates, and practically speaking, would result in a lot of calculation errors if our model were to run on an actual quantum computer. QNetGAN has far fewer quantum gates, making it much more efficient, and only uses 3.4 gigabytes. As mentioned earlier, this model has resulted in 141 chemically valid molecules, meaning they've satisfied the rule of 5 out of 300 generated molecules. And although this model's accuracy is at 47%, we plan to increase this with our research that we will mention in the next slides.
So to improve the accuracy of our QNetGAN model from 47%, we're implementing several post-processing molecular geometry optimization algorithms as indicated in the figure. Starting from the generated molecule, first we have Lipinski's rule of 5, which are a set of guidelines used to determine how successful a potential drug molecule will be based on factors such as molecular weight and the number of hydrogen acceptors or donors. Next, we have the Octet Rule, the hydrogen addition, and formal charge algorithms, which are all completed and will be further explained in the next several slides. The algorithms after that, which are currently in progress, start with optimizing the bond angle and length. Then we identify if a molecule is cyclic, and if so, it is processed through a separate algorithm to account for its structure. Through these algorithms, we output XYZ coordinates to represent the optimized chemically feasible molecules. So the first algorithm we have is the Octet Rule algorithm. The Octet Rule states that most atoms tend to have 8 electrons in their outermost electron shell, which provides stability and reduces their reactivity. In order to implement this algorithm, we chose a DFS algorithm because molecules often have depth-dependent relationships, and this algorithm traverses through each atom and a bond of a generated molecule, starting at the root node and exploring as far as possible along each branch before backtracking. The workflow for the Octet Rule algorithm begins with us representing an outputted molecule by its atoms, bonds, and electrons. Next, we modify this molecule by adding missing hydrogens before it's ready for the Octet Rule validation. To check the molecule, we traverse through it completely before checking whether there are still any open orbitals. If there aren't, the Octet Rule is satisfied, and we continue with our workflow.
Our next post-processing algorithm is our hydrogen addition algorithm. We've encountered a problem with our generated molecules, which is that some of them are missing hydrogen atoms. And this is fatal, as this means the generated molecules will fail to satisfy the before-mentioned Octet Rule, essentially meaning that the atoms in the molecule will not have 8 valence electrons to fill their outermost shells, leaving the molecule less stable overall. Thus, to fix this, we added an algorithm that calculates how many hydrogen atoms are necessary to fill the valence shell of each atom in the molecule and add any missing hydrogen atoms accordingly to ensure our molecules satisfy Octet Rule. You can see the general workflow of our algorithm on our slide, which follows a DFS structure explained previously. Essentially, our algorithm employs an adjacency matrix to determine the connectivity and bonds of a molecule, which aids us in determining whether atoms are missing. After employing the adjacency matrix, we determine each atom's explicit hydrogen/bond count, and then from there, we determine the number of missing hydrogens from this count. From there, we create the empty adjacency matrix, iterate over each atom and calculate their valence, and then add the missing hydrogen atoms and proceed on to our next chemical post-processing algorithm.
All right, so for our next algorithm, we're focusing on an aspect of a molecule called a formal charge. I'm sure a lot of you are familiar with this algorithm already, but it's basically the number of valence electrons minus the number of non-bonding electrons, and then minus the number of bonding electrons divided by 2, which is also known as just the number of bonds. And then the closer that these formal charges are to 0 overall, the more stable a certain molecule is. A set of generated atoms can be bonded together in multiple different ways. So these formal charge calculations help us determine which structure is most optimal in creating a stable algorithm. This algorithm was successful on 100% of the molecules that we've tested it on so far, but in the future we plan to test it on more molecules, as well as use it for our intended purpose, which is generating different molecular structures so that we can compare them using the formal charge calculations.
Algorithm is our molecular geometry optimization algorithm, and it is one of our most recently added algorithms. Essentially, molecular geometry is a category of geometries such as trigonoplanar or bent that are assigned based on the number of lone pairs a molecule has. And essentially, it aims to convert the adjacency matrix output given from the previous algorithms into visualizable XYZ files. This involves finding the molecular geometry, or basically the three-dimensional structure of the molecule. Various molecular geometries include, as mentioned, trigonoplanar, trigonoidal, bent, and tetrahedral. First, the algorithm identifies the molecular geometry at each point based on bonds and non-bonding electrons. And the examples will be shown in the next couple of slides. After identifying the molecular geometry, the algorithm references a database of average bond lengths and angles in order to construct the molecule. Then it traverses through the molecule using a DFS algorithm and constructs an XYZ file one molecule at a time that documents the coordinates of each atom based on the bond lengths and angles, as well as the molecular geometries. Finally, we'll visualize our completed molecules using Avogadro, which is a molecular visualizer.
Okay, so let's take a look at an example of this algorithm at work. So as you can see in our first screenshot there, we have an adjacency matrix. This is of a CH4 atom where one carbon at the top is bonded to 4 different hydrogens, as you can see by all those 1 bonds there. So basically our algorithm will go through and calculate that this is a tetrahedral molecular geometry, and then it'll go through and create an XYZ file based off of that. So as you can see, it gives the carbon a coordinate of 0 and then the hydrogens coordinates surrounding that, so that it forms the molecule that you see in number 3, the 3D visualization. So that's what it looks like if you put it into Avogadro or any other molecular visualization software, and it shows up in 3D. If it were spinning around, you'd be able to see that it's actually in 3 dimensions, but I think you can tell from the picture.
For our last algorithm, we have a cycle detection and coordinate calculation algorithm. Almost 90% of our molecules in QM9 are cyclic, which means that we have to accommodate to the differences of their structure. To have accurate geometry optimization, we made an algorithm to see if a molecule is cyclic based on the position of atoms in the ring of molecules. At first, there are 0 atoms visited, and then the algorithm goes through each atom, and if it reaches the one it started with, it will print cyclic true, and if not, cyclic false. Furthermore, like the other geometries like square, planar, tetrahedral, etc., we coded for the different structures of cyclic molecules. Here are some of the examples of how the structures look like on the slide. Our code uses math to find the bond lengths with the known bond angles. Lastly, it assigns it XYZ coordinates to each atom to provide the accurate 3D visualization of the molecule.
So these are the molecules we've tested so far. They only contain carbon, hydrogen, oxygen, fluorine, and nitrogen, as those are the only molecules in the QM9 dataset. The molecules we have tested also include carboxyls, hydroxyls, aldehydes, and some alcohols, and other molecules made with similar elements. We plan to include additional molecules and elements in further iterations of the algorithm. The molecules in the post-processing algorithm begin with the molecular formula, which are then converted to smiles. So you can see C6H6 is benzene converted to the smiles representation. And the smiles are usually converted to adjacency matrices, which are numerical representations of bonds in adjacent atoms. Properties of individual atoms are then added in the atom vector part of our code. This includes, but is not limited to, atomic number, atomic mass, symbol, bonding, electronegativity, formal charge, and hybridization state.
So currently we are working on an upgraded version of QNetGAN, which will incorporate some of the helper algorithms that we have already developed, along with some new features. So to improve stability and increase speed during training, we implement QNetGAN 2.0 with gradient penalty. And we also added, well, we also are going to add graph convolution on layers. Since these layers are specifically designed to work with graph structured data, they do this by capturing relationships and interactions between nodes, such as the types of bonds between different atoms, and this makes them very effective for chemical molecule structures. Combining these layers with the LSTMs inherited from the original QNetGAN, we hypothesize will allow the new model to handle temporal graph structures even more accurately. As QNetGAN 2.0 is still in development, we have very limited results, except for the piece of modern art shown on this slide. You can tell it's not a very realistic molecule because there are a lot of triple bonds, and the fluorines are doing some really weird things. To fix this, we are also working on implementing an octet penalty, which would penalize the generator for producing molecules that do not satisfy the octet rule. This would be calculated using the formal charges on the individual atoms and the number of hydrogens that we need to add to make the molecule satisfy the octet rule. And this would be calculated using the hydrogen addition algorithm. We expect that this will motivate the generator to produce more chemically valid molecules instead of modern art. The molecular post-processing algorithms that were mentioned will also be merged with QNetGAN 2.0 once it is complete. For more information about our future works, head on to the next slide.
So as you can see, there are a lot of different parts of the project being worked on simultaneously, from the development of new generative adversarial network models, all the way to the development of various molecular geometry optimization algorithms, like the formal charge algorithm, molecular geometry calculation, cycle detection, all the way to molecular dataset testing generation. So we hope to combine all of these into one thing in the future by integrating all of our molecular geometry optimization algorithms directly into the model training, which we've already begun doing in the previous model that Max was just talking about. But to do this, we will penalize the model whenever molecular bond lengths and angles are not optimized, or if the model chooses a structure that does not properly optimize the formal charge of a specific molecule. In doing so, we hope to increase our accuracy to above 80%. Beyond integrating all these algorithms directly into the model training, we are also exploring other types of models, including the variational autoencoder model, as well as QRNNs. Linda will be talking a little bit about the VAEs on the next slide. Furthermore, we are going to continue our collaboration with the quantum chemistry group to build in molecular calculations into the QNetGAN. Thus far, we've been working quite separately and independently on our own respective parts as we prepare the generated molecules for their use. But at the moment, as we begin to near the end with more and more results and more valid molecules, we hope to be able to further our collaboration in this coming semester. Lastly, we hope to run our quantum algorithms on real quantum hardware as an inspiration from presenting at the IEEE International Quantum Conference earlier this year. In doing so, we expect the efficiency and the resource usage to improve significantly, as we will actually be able to harness the quantum mechanical principles for computing advantages.
Okay, so before we close off for today and open it up for questions, I just want to talk a little bit about quantum variational autoencoders, which is another model that we're thinking of implementing in the future. So what is a variational autoencoder? It's basically an autoencoder, which is something that encodes and decodes data, as you can see in this graphic on the right side. It takes the data, it compresses it into a point basically, and then it pulls it back out into a decoded form. The difference between a variational autoencoder and a regular autoencoder is that the variational autoencoder, instead of encoding things into a point, it'll encode it into basically a Gaussian or a normal distribution over a latent space, which you can see on the left over there. And then once you sample from that latent space when you're decoding it, you'll basically get unique different results. So for example, if you encoded this orange triangle and a blue circle and a green square, then you can sample from any point in between those and get something that is partially a bit of each. And that's basically a way of generating some new data, which would be molecular graphs in this case. So we plan to implement this model within the next few months and incorporate quantum computing concepts into it, and then compare it to our original models, including like the original QNetGAN, the QNetGAN v2, and then compare them in terms of accuracy and computational efficiency and see what turns out to work out the best.
So we would like to give our thank yous to several people, including our research advisor, Dr. McMahon, for his guidance throughout this project, Neil McMahon for all his help in dealing with any server-related problems, Dr. New for his guidance on chemical resources that we could utilize, including papers and stuff like that. ASDRP for giving us the research to conduct this high-level research and to share it with you all. We would also like to thank our ex-group members like Diptanshu Sikdar, Arjun Bamra, Satvik Prasanna, and Joey Hua, as well as the quantum chemistry group for being amazing collaborators. On the right, you'll see several QR codes, including links to our references and several papers/proceedings that we have presented. So thank you guys so much for attending our talk. We're open to us answering any questions.